Hello folks. So in this video I wanted to talk about inodes and file systems. So let's actually continue where we left off. So we were talking about file systems, specifically some set of file systems, that is file systems in Unix like systems, Unix like basically kernels. For example, Linux, Unix, Darwin and all. So example for such a file system is ext4. So it's called extended fourth. Let me show that ext4. So fourth extended file system, right? So in these file systems, there is this concept called inodes. Inodes are basically a data structure and this data structure is only present in some file systems in Unix like systems. So inodes are the place where file systems store metadata for files. So file systems take care of bridging the gap between the operating system and the storage device, let's say hard disk drive. So basically you can see here that a file system is a method an operating system uses to organize, store and manage files on a storage device like a hard disk drive, or SSD is short for solid state drive. Let's stick to hard drive for now. Let's stick to physical storage and file systems on top of physical storage instead of something like network file system where it's about networks also. So now inodes are basically a data structure for storing metadata, say size, permissions, owner, created at, updated at timestamp, like all those things. And file name is not there though. And we are looking at how does it look like in say Darwin, for example. So this is Darwin. So you name. This is Darwin kernel. And here I was actually trying to show that there is a list of directories in a file, and if you just do ls-i, it will show you the inodes, which are unique numbers for each and every file or directory. So inode has a unique number, and basically inodes store the data around where the data blocks are present, basically pointers or the address to the data blocks in the physical storage. So inode has that detail. So just a minute. I think that's all clear here. And separates name, data location, yeah. And yeah, it's file systems specific. Not all file systems have inodes. And also within a given file system, inode, the numbers are unique. But across file systems, even if they're the same file system, you can have the same inode number across file systems, right? So now I'll show you the inode numbers. For example, these are inode numbers on Darwin. This is actually not ext4 file system. I was just checking out the mounts. This is APFS, which is Apple file system, and I think they also had some older thing called I think HFS something. So if you look at the -t, just a minute. So if you look at this, they'll talk about some HFS, which is not Hadoop file system, which is also a thing, but it's something around an older file system that was present in older like Apple systems. So APFS is Apple file system. I don't know what is AutoFS. Let me check it out. So APFS, you can check it out here. So Apple file system. It's a proprietary thing. So for SSDs and flash storage versus HFS. If you simply put it as that, so you notice that HFS plus is the older thing designed for spinning hard drives, like hard disk drives. So and then there is AutoFS. Let's check that out. So it's a Linux service that automatically mounts file systems like network shares, okay, on demand when accessed and unmounts after. Interesting. Cool. It sounds like a Linux service, but looks like it's there on Darwin also on macOS. If we'll come back to this later maybe. Right? So maybe I will write it down as a thing to explore. Things to explore. AutoFS file system. Different file systems basically. Different file systems. File systems is a single term. AutoFS file system, and there is also ext4. So I'm not going to go too much into detail around them because, for example, ext4 has details around it, like how it is bridging the gap between, like, as a file system, how it's sitting in the center between the operating system and the storage device. So the physical storage device, and how the operating system organizes and stores the files using a file system on the storage device. So if you simply look at file system, you should see that file system helps with organization, storing, and of course managing of files. So ext4 apparently has some improvements over its predecessor. So it's a successor to ext3, and I think there's also ext2 and all. So there's something about fragmentation and whatnot. So we'll check it out. What is fragmentation in the context of physical storage, HD, etc. Does it apply to SSDs? What is it in the context of file systems? So these are some things we'll ask, and we'll look at say something like ext3, and I also noticed some more like XFS and then BTRFS. I think it's short for B-tree file system, and we'll also look at Hadoop file system for later. Right. So let's get back to inodes. So we were looking at inodes in macOS and Darwin, and you can actually check out the thing using this also, df-i. Just simply typing df also shows you this, by the way. So it looks like the output is the same for df and df-i, but df-h alone, it shows properly in human readable format, and it shows IUs, which is basically inodes used, inodes free, and the percentage of inodes used. And basically here, this is in Darwin. So here I'll look at it in Linux. So here I'm in a playground machine Linux online. It's a micro VM. So here I have some dummy file and a dummy directory. So if I say ls-i, ls-il, you'll notice that this has inodes, right? These are inode numbers. This is for the file and this is for the directory. And if you look at the different file systems mounted on this, there are a lot of them. So specifically, if you want to look at it, so these are all like, there is this thing called proc file system, and all like proc, and then sysfs. Some of them are like virtual file systems. So we'll get back to that later. Virtual file systems, proc fs, sysfs, right? There are some more. I think C group, tmpfs, and there are some more C group v2, a lot of them. We'll come back to these later, but basically C group 2 and tmpfs and tmpfs. There are some more. So I don't know if these are also virtual file systems. Something to check out. I know that these are, yes. Need to check about these virtual file systems. Let me just put them separately over here. So I'm looking at only Linux. So yes. So here I'm gonna actually look at. I'm currently in /home/labyrinth, which is basically this. This is the only file system on this. So this is like ext4, and this is the device, and this is the ext4. So I can actually see that. I think if you mention this, you'll get only that. Yeah. So if you mention sysfs, you will only get those file systems. You give the type, and you'll get only those. So ext4 file systems, there's only one, and this is what is mounted here. And well, if you want to actually see the disk space on this one, you just say df and say df-h. You see that it has some 40 GB in the root, out of which 36 GB is available. Here inodes don't show up directly. You have to say -i, or you have to say -inode, and you should see how many inodes totally are there. Basically, how many, like, this is fixed given a file system and a physical storage drive. When you create the file system or like format the file system, you have it. It's like fixed number of inodes, and how much of it is used and how much of it is free. If I actually go ahead and let's say touch say kp1.txt, you can actually see that this will reduce. The free will reduce from 2476341 to 2476340. So like this, if you want, you can actually exhaust all the inodes by simply creating files of very small size. For example, kp text is just 0 bytes. Okay, so you can also create 0-byte files by doing this also. So kp2.txt. So kp_.txt, you will actually see that these are 0-byte files, right? And you can create a lot of these, and you will notice that it will just use up all the inodes like that slowly. I even asked some AI systems, for example Perplexity and then ChatGPT, to actually exhaust the inodes, and they did a pretty good job. So let me show you what they asked me to do. Basically, they asked me to create multiple files, that's all. So so Perplexity told me, 1 minute, how to exhaust. So for it, Perplexity told me to do a safe test, and then do this. I didn't create any temporary file system, test file system and all that. Instead, I went into the existing file system that I have here, because this is a whole playground. So I just used that, and just ran this in a bash script. I created a script. I didn't put sequence though. Sequence is some command to, let me see if it's there in this also. Sequence 1 to 5 to 8. So sequence is a command, looks like it's there on Darwin also, commands print sequence of numbers, but in Linux also it's there. And here you can actually see, let's say sequence 3 to 7. So yeah, instead I actually just used for loop with curly brace over here, and put 1.1,000, and it created. So I was actually putting millions of files, but here they actually create some 1,000 directories, and inside each directory they put sometimes 1,000 files, finally to create like 10 million 0-byte files, right? And this takes quite some time though. I even tried to put ampersand here. For example, let me show this to you. The different ways that I tried to follow, do this. And I was trying this out on my own, and this AI also said the same thing. But I also noticed some interesting things from the AI, like how to create a temporary file system, which is something that I haven't done before. So let's go ahead and create a bash script here. So I'll just say instead of this, I'll just say, and this is the best version. I don't want the best version first. This is like the best version. Exhaust, let's say 3, right? I want exhaust to look like, just a minute. This will take quite some time to run though, so beware of that. This is 100. I'll just say KP. I actually did echo or something, I think. Instead of this, I actually did echo, and since I didn't want a new line, I just put this and just said kp dot txt, right? So this is what I had written. Let's just copy this out. So again, I'll just say exhaust, and I'll put this in, right? And I'll just run this, right? So here you can actually see exhaust is the thing. It creates 100 files, right? So it will just run exhaust, syntax error, echo -n. I think I need to put a semicolon here. Yeah. So, yep, it's done. Oh, it created it like this. Just a minute. For loop bash for loop. So list of items. It should say in. It's 2 dots, not 3 dots. Sorry, it's 2 dots. So let me get that. Is this the same thing? Yes. So remove this and bash exhaust. Yeah. So I have 100 files here, right? So kp 100 here. Yeah. So I can actually remove all of these. Actually, I'll move the exhaust to outside. So this should go away. It's okay. Exhaust. Yeah. So you cannot just run exhaust just like that because I didn't put the permissions on it. So if you just use it, it will say don't have permissions. Permission denied. Even if you do sudo x whatever, because permissions are not set on it. So if you just put chmod +x, you can actually check it out how it looks like. So it's read write only, and you can just say chmod 744, and then you can do exhaust and it should run. So now what I'm going to do is basically, I mean I can just run it as like this. I'll do that, but instead of this many, I'll look at how many free inodes we have. So I'm just going to put this number as it is over here. It's a very big number. You should see how much time it takes to actually, run this. Right? So I'll just say bash exhaust and let this run, and I'll show you what's happening on the directory. So here I'll remove these. I'll remove the readme also. And dummy is where our files are there. So it's taking actually a lot of time. Basically it's stuck actually now if you see. Interestingly, this is stuck. Okay. So it's just doing echo, and it's creating a lot of files as you can see here. I had opened it, so I am going to close it, and it's creating a lot of files. Let me see if I can actually just open up. Maybe it was a bad idea to run it. I can actually get hold of this. I can't even close it. Okay, close it. Let me see if I can get access to the terminal here. No, even this is rolling. So terminal, no, this is stuck. Cool. Okay. We got it. Let me just run PS. Okay. Looks like the thing killed it. Good. I think the system ran, and like behind the scenes, I think the playground system ran some commands and checked it out. For example, you can actually see folks that you can actually see a lot of commands being run behind the scenes to check different processes running. So to make this faster, I think this is pretty slow, and it created a lot of files though. As you can see, it created a lot of files. I'm just gonna go ahead and do this. Argument list is too long. Okay. I'll just say 9. It takes a lot of time to actually do that, but we can actually see how much inode is being used here, right? So 27% I used it up. If I start deleting some of the files, you will notice that it's reducing, right? So it is pretty slow. Actually, the last time I ran it on a Linux machine, it was pretty slow. What I did over here was I just put an ampersand symbol over here. So that's what I did. So let me just copy paste this over here. Give me a moment. Cool, I'm back. So I created some more versions where I put an ampersand symbol over here, and then I created a version where you just use this, and then one version where you just create directories like this and just use it up, right? So let me actually show you this version. This shouldn't be that crazy. Let me actually put this with exhaust file.sh with the ampersand symbol, and okay, right. And you can actually see all the commands running on. Install forkstat sudo just a minute. Sudo apt update. I think it's taking some time for some reason. Anyways, yep, it's done. Install forkstat. Yes, it's done. Cool. Now, if you actually run forkstat, you will actually notice that a lot of commands are running here. You'll notice that as you can see over here, a lot of commands are being run. They keep checking what are the different processes running. I think they keep running it. So yeah, and as part of this, we are now going to run the exhaust. Let me go into this dummy. Make directory dummy, and this say bash exhaust. So this should create a lot of these. As you can see here, it should just create a lot of files. And if you look at df-i, you should see it being used, but a bit slowly over here. You'll notice that it's reducing over here, right? And a lot of processes are running, so I'll just stop it now, and I'll just stop this also. So here you can see exhausts ran a child because I put ampersand, so this will run a child process. You can see how it created one directory, another directory, and so on, each with 10,000 files because I put 10,000 here, right? So now you can actually get from these. You can actually see that the inodes count has decreased 2465659 to 2461817, and yeah. So if I actually remove all the files here and actually say df-i, now you should actually see that the inode percentage usage is 2 now. It was previously 3, now it's only 2. So, and what else? So this is about inode's exhaustion. The interesting thing is inode exhaustion does not happen to all the file systems. So just before that, let's check it out on a test file system. So the other what do you say, AI that I used was ChatGPT, and this is what it said. It just said to keep creating a random file, but this can give the same value again and again also at times, like not immediately, but let's say it gives 1, after some time it can give 1 again. So I didn't want to use it. So faster exhaustion, I don't know how fast this will execute, but this is what 10 million I think it's 3 zeros, yeah, it's 10 million. So it's just asking you to run and create 10 million files, or use nested directories, and use containers, which is more safer is what they say. And how to record, just clean it up. So the thing is, you can actually set inode limits. So I mean that is also there when you create the file system, that is, right? So for example, just a minute, see inode settings, not count. So you can actually say these many inodes is what I want, right, when creating a file system. 1 inode per 4 KB and all that. So based on the size of this thing, basically you have data blocks. So you're saying I think 1 inode per 4 KB. Let me see. So this is actually to make file systems, mkfs.ext4. If you actually check out mk, there'll be multiple mk, like of course make directory and all that, and then there is mk2fs, which is to create an ext2, ext2, ext3, ext4 file system. And actually when you use what do you say, mkfs.ext, it basically runs it with -t over here. The type is that. And so basically if you do which mkefs mke2fs, it will say this. And if you say mkefs dot e ext2, ext3, ext4, right? So if you actually look at this, you'll notice that it's pointing to this one. So it basically reads that this is the this basically reads the program name that is being run and then uses that to define its flags. So you can create file systems like this ext4, and that is basically mentioned in Perplexity how to do that. So I was actually creating that today. So 1 minute. Yeah, so basically I created, you need to create a small file which is of what do you say, this is actually 1 GB file. I'm going to create a 1 KB file, okay? So dd, so man dd, so dd is basically convert and copy a file. There is input and output. So input file, and then there is also output file, and there is also BS bytes. So read and write up to at a time. Default file overrides IBS and OBS. Read up to at a time default, and what is OBS at a time? Okay, so let me write this down. Test file system .sh. Right, so this one, instead of 1 MB, I'm just gonna say 1, right? So this is that many, 1 byte, right? And I have 1000 bytes, which is 1 KB, right? Is that fine? I think this should be fine. Let me try this out. My FS, right? So if I do ls-alh or ls-lh, I should see that my FS is there, and this has 1 KB, right? So this is a file that I can use, and by the way, there's nothing inside this file. 0 bytes, as you can see here, it's just simply 0 bytes. 1 minute. Head. Same is true for like basically from dev 0 or dev null, whatever you do. So so just a minute. There's also dev null. If you just do ls-alh, you will notice that this is some sort of weird thing, and you can't write to it. I think abc, it just goes to nothing. Yeah, so if you just do inless is not a good idea. Anyways, I tried that today afternoon, and it just got stuck because a lot of just bytes, empty bytes coming up, because it just indefinitely gives thing. Like I think there is dev 0 and dev null. Dev 0 and Linux dev 0. So basically, it's a special pseudo device file in Unix like operating systems. So any data returned to the user is discarded, similar to dev null. So that provides an infinite, endless stream of null characters, binary zeros, null bytes, right? Data sync. You can also put anything. It's like a black hole, like the data is simply discarded without it. And powerful and tool often used in conjunction with utilities like DD, creating files of a specific size and all that. Very large file, if you want, you can just create that, right? And can be memory mapped into a processor's virtual address to obtain 0 filled in anonymous memory bases. Cool. Versus dev null is a data sink black hole that discards all input and provides no output. It provides is a data source, so it provides an endless stream of null bytes when read. Reading immediately returns end of file, dev null. Okay. This one produces continuous infinite stream, okay, zeros. Writing, it just discards. This is also discarded, right? Primary use, suppressing unwanted output to null, creating files of a specific size. Okay, so you can read from this, you can't read from this basically. Right, so if you just say cat dev null, nothing should come up. But never do cat 0. Okay, looks like my playground is over, so I'm just gonna go ahead and use my playground over here. So let's start the playground here. Okay. So if you just do cat this dev 0. Not a regular file, use -f to see. So you can see over here how it's like Yeah, I think it's already full. So basically now we're looking at just a minute. Let me actually create that. This. Let me create this. So we have ls-lh my_ls. Now what we do is we create a file system out of this, right? So basically you do mkfs ext4, or you can do this mke2fs, and inside this file it just creates it. Okay. Attach the file. Some setups instead attach the file to dev loop and with loosed up and run this. So basically this happens automatically. I think in my case, for example, here when I actually put this in, so it says inode size 256, inodes count 0, too big for a file system with 0 blocks. Specify higher inode ratio -I or lower inode count -N. Okay, so okay, inode size, inode count is 0. Can I have 2? No. Okay, so I need a bigger file basically. So let me just create a bigger file. So let me just say 1 MB then. I'll just say 1K. Okay, it's 1 MB. Let me create this. So it's created. So it says file system too small for a journal. Discarding device blocks done. I need to check that out what that means, journal. But allocating group tables done. Writing inode tables done. Writing super blocks in file system accounting information done. So now if you actually look at the dev thing, right? Okay, so let me actually so here they say mount this. So when I do this, so when you actually create a directory, let's say you create a directory mnt, so you need sudo access to this, and you can't just look inside this. Okay, you can. Great. So now what you do is you just mount this here, right? Sudo mount. Once you mount this here, you should be able to see these files, right? So you have a file system over here. Initially there was nothing in my loop. Now you have some lost plus found and whatnot. If you actually check out df-h now, df-i by the way. So here you should notice that it says dev/loop0, right? So I think this happens automatically. At least the file system, it says loop0 because it understands, I think, that it's a loopback file system, because that's what they call it as. They call it as a loopback. 1 minute. Loop. Yeah. A loopback file system created with the file and mkfs.ext4, right? So I learned that. No, 1 minute. So I was asking what's a loopback file system. It's a virtual file system created from a regular file, where that file is treated as if it were a real disk or partition and then formatted and mounted, right? So from a file you think that the file is the disk and it were a real disk or partition, and then from that it's formatted and mounted, right? So looks like this is how you do it. Basically you format it like this using dd if you want, put null bytes and all that, and then mount it, right? So now let me actually note down these steps before I forget. This was too small, right? So we just use this. And then check this out, right? And then finally check the mounts. If you actually check the mounts, you should be able to see this loop back. Let me see if I can find it right. Grep loop. Yeah, there's a thing called this. Yeah, it's on the bottom most. Yes. So basically mount it. So you do the sudo this thing, and then sudo mount myfs.img, right? So that's what we've written here, right? And then ls right? And you can see the number of inodes now on this file system, which is actually only 179 inodes are free. Now it's very easy to exhaust this, because now let's say I go to mnd loop, right, and basically my loop. So here, if I actually do make direct like touch readme, okay, I don't have access to create things here, so let me just labyrinth my loop, sudo this put as so this will do, and now I should be able to go and let's say this myfs is basically what you do here, and this make it this is fine, and now I can just try out things like grep, look for this mnd loop my loop, right? And now if I actually touch readme.md, if I see this, it should be 116 like this. Now if I actually exhaust it, let's say I just do exhaust exhaust. Let me see where is it. Okay, I think I don't have the exhaust thing now. Let me create it. Exhaust sh, and I don't even need the crazy ones. I can start with this. In a few minutes it's literally gone. In a few seconds I can actually do this. And bash exhaust. So it says no space left on device, as you can see, right? So it has run for multiple of them. So ps logs, so you can actually see that it said no space left on device and all that. So ultimately you can actually see that on the top, right, it had some space. It was creating files for some time, and then from 116, exactly 116, right? So I think we had one. Um, I mean, I created exhaust, so but then that was on a different file directory. So we had 116, so clearly from there it started failing. So if you can actually see, you will have directory 1 with file 100, 110, 110. So let me file 116, right? It's 115. Till here it came up. File 1 was the start, and directory 1 is also created. So basically, directory 1 will use up 1, and then remaining was all 115. So then 115 files, and that's it. So now if you see, no inodes are free, and you used up all the inodes. Now if you want to create any files, you just have to go ahead and delete all the existing files, then only you can create it. So just a minute. Example.log. Right. Cool. So now I also wanted to do some more things. Let's see. So I showed you that you can actually exhaust the inodes. The next thing is how do you basically set inode limits. So you can actually see that inode limits are part of the ulimit thing. So man ulimit, okay, there's no entry for it. But if you say -a, it will show you all the limits. One of the limits is for the files, right? So you can actually see the file size and open files. So if you actually tell that the number of open files, like how many number of files you can open or create, that can reduce the number of files, and in turn you can actually just reduce the inode usage, right? So one minute. Inode limits, you can also set it like 1 minute. See inode settings. Okay, let's see if this works. There's DA, okay, df dev root. Dev root. Okay, interesting. We'll come back to that. So you can actually mention the inode count, and if you don't want inode issues, basically, right, where you exhaust the inodes but then you still have disk space remaining, you can actually go for other file systems also. For example, there's this file system called XFS, which has dynamic inode allocation. So in ext4, inodes are created beforehand itself. It's a fixed number of inodes, right? So it is good when you have like the number of files is less. ext4 is good, but XFS, you cannot change the inode, like ext you cannot change the inode count after creation. In XFS, the inode is allocated in a dynamic manner, right? So for example, let's see how you can actually create this. So maybe I'll do that in a different lab because this doesn't show much of that. XFS, I need to create it and check it out and see how it works. But basically it's supposed to actually help you with ensuring that if you have this space, you will still have inodes that you can create. Unlike ext4, where the number of inodes is different and it's limited. So, and you can exhaust the inodes without exhausting the disk space. but that is hard to do in XFS. And there is also one more file system and probably many others where there is no concept of inodes, right? So let me see if I can find it. Yeah. So I was asking how BTRFS compares here. Let's compare BTRFS. So BTRFS I think is short for B tree file system. Yeah. So BTRS tree file system is a modern advanced copy on write file system for Linux, designed for scalability, data integrity, fault tolerance, easy administration, multiple things. So specifically through the lens of inode exhaustion, so big picture, it does not have a fixed inode table. Inodes are dynamically allocated as metadata objects. So inode exhaustion almost always coincides with the actual metadata space exhaustion, not an artificial inode limit. So in BTRFS, so fundamentally different because it doesn't even think of classic inode table. So how it stores inodes, basically there's no inode per se exactly. I think it's called it puts it in double quotes. So if you look at it, it basically has items in a B tree and it allocates them dynamically, similar to I think XFS. There's something to check out. I think I wrote this down. Things to explore. BTRFS, yes. So different file systems. So basically create files in a XFS file system. Understand dynamic inode allocation in a BTRFS file system. Create BTRFS file system. This is XFS. So allocation in the B tree, right? And yeah, for now that's it. So they have some visual mental models for it, how the inodes are stored. So how you can actually avoid inode exhaustion and all that is mentioned here. So and yeah, you will of course notice messages like this for no space left on device metadata. So and interestingly they put Nginx over here, but this is not Nginx, it's CSS. This is actually bash on the logs. So metadata versus data space. So internally separates data chunks, metadata chunks, system chunks. New files cannot be created even if data chunks are free. So, and yeah, there is a recommendation on what can be used there. Like XFS is supposed to be the safest container default. BTRFS is powerful but sharp tool, and basically inode exhaustion is a ext4 problem. Metadata exhaustion is a BTRFS problem, both avoided in XFS. So there's more, but basically they talk about Kubernetes and all, where like Kubernetes and Docker avoid BTRFS by default, and because like fragmentation and stuff looks like it. So we need to check this out. Why and where XFS and BTRFS is used, and why ext4 is used, right? Also, that's all I had for this video. Trying out some file system stuff and reading through some inode stuff. So I would totally recommend trying out AI just to learn things and just play around and see how it works out. And yeah, I think I also noticed one more thing where it is element. Yeah. So I actually noticed one more thing, how to prevent processes from creating excessive files. You can use this thing called PR limit. Just a minute. Example. It's called PR limit. So looks like it's a process limit thing. So get and set process resource limits. So for a running process, we're using its PID, or to run a process and to tell that these are the limits, right? So you can have limits like number of files, for example, no file, maximum number of open files. I think no is short for number, not for no file. And then there is of course number of and CPUs and CPU time in seconds, number of processes and whatnot. So you can do this on a running process. You can set it. I wonder if it will actually be able to set a limit, even though the limit, it's already created many more than that. I don't know. Let me try this out. Something to try out. 1 minute. PR limit, set process limits for a running process where the process has already used the limit, exceeded the limit to be applied or exceeded the limit. I think it might does give errors for like number of processes, number of open files and all. Right? What else can you do? Let me see if PR limit is available on this. It's only on Linux, I guess. Man PR limit. So yeah, that is that. So you have CPUs, maximum data size, interesting. There are a lot of stuff. Address space limits and whatnot. And you can also, I guess, look at these over here also. I wonder if they have locked memory. Okay, address space, I think. What else about file locks, max user processes. So this is for the number of processes it can create. So yeah, this recently I was using this. Pipe size, open files, file size, scheduling priority and whatnot. Cool. So we can try that out, like how you set process limits. You can do that, and then you have inode quotas, user quotas, similar. Looks like there are some stuff for that to limit that. So this, I think, -n is for open files, yeah. So that way you can say how many files, or in the limits conf you can say no file. Instead of nproc or number of processes, you can say no file, or like number of files basically. Yeah, and you can use you can monitor and alert based on thresholds, right? And loopback file system, we checked it out. There are other things, we'll come back and check it out, like fragmentation and whatnot.